this video we're going to look at the harmonics for closed pipes. Now when they say closed pipes, really what they mean is pipes which are closed at one end and open at another. So we deal with pipes which are open at both ends, which was the last lesson, and then in this lesson it's closed at one end and open at the other. So the rule with the closed pipes is that where the pipe is closed, the end where it's closed, which is this end, will always have a node. And that's just what you need to remember. There's always a node at the closed end. And just like yesterday, the rule at the open end is you will always have the opposite of a node, which is a antinode at open end. So it's similar to the last one. When we're looking at the different harmonics, we can draw an example of a wave, standing wave. And if we want to find the first harmonic, it's going to be from the first point here to the first node here to the first antinode, which is here. So that's our first harmonic drawing. That's our fundamental frequency. Or our first harmonic. And you should be kind of used to what I'm doing here now because we went through it in detail in the last question, or the last lesson. Now there is something that you need to kind of know about this that's different to the other ones. Let's say we call the length of this pipe L. Well, what is L in terms of a wavelength? Well, one full wavelength would be one full peak and one full trough. So what we see here in this red line is we see a quarter of a wavelength, or lambda over 4. So we can actually write the wavelength then in terms of L. The wavelength will be 4 times whatever L is. So if you know that this pipe has a length of 2 meters, well, the wavelength of that wave is going to be 4.2, which is 8 meters. So that's one way we can figure out the wavelength. But let's say we just figure out what the fundamental frequency is using our wave speed equation. Now our wave speed equation is c equals f lambda. So the frequency is c divided by lambda. C is the speed of the wave, but we leave it as c, divided by lambda, which is 4L. So there's an expression for our fundamental frequency. Now that doesn't look like much use to you now, but wait a minute and you'll see where we use it. So now let's look at the next possible harmonic. So we have our pipe closed at one end and open at one end. We're starting with a node, and then we'll keep going until we get to the next antinode, which is here. So that's our pattern from here to here. So let's draw that in. Something like this. Again, we have a node at this end, node displacement, antinode at this end. If we were to look at this in terms of wavelength, our L would be 3/4 of one wavelength. So one wavelength then would be 4 times L over 3. So if we knew that L was 2 meters long, multiply by 4 and divide by 3 to give you what the wavelength is. By the way, I didn't write it down, but this is our second harmonic. But you should know that at this stage now, follow the pattern. And our second harmonic is also known as our first overtone. Now let's go back to this equation here. So let's do the same thing to find the frequency for case number 2, our second harmonic. C equals f lambda. So our second harmonic, let's call our first harmonic f1. Our second harmonic f2 will be c divided by lambda, which is c divided by 4L over 3, because lambda equals 4L over 3. I have that written down over here. You can rewrite that as 3 times L over 3 times C over 4L. Now why am I doing this? Well, if you look at this equation for F2 and you compare it to the first equation for F1, this bit here is the same as F1, C over 4 times L. So we could rewrite this and we could say, well, F2 equals 3 times F1. Now why is that important? Well, that's different to the other cases that we've been. This is telling us that we've seen. This is telling us that the second harmonic is 3 times as much as the first harmonic. So if the first harmonic was 20 Hertz, the second harmonic wouldn't be 40 Hz like it has been in the last case where we had open-ended pipes or the string. The second harmonic would be 3 times this, which would be 60 Hz. And that's important, that's different, and that's something that they'll tend to ask. Now I'm going to do one more very quickly and you'll see that this pattern continues. So if we do another one, and again I'll do it quickly because you should have the point here. If we draw the next harmonic, it's going to go from the first node all the way to the here. And skip the first antinode, skip the second, third antinode. And that will look something like 1, 2, 3. Something like this. Now that's a bad drawing, but this is in your textbook on page 201 where the drawings are a bit better. Again, the length of the pipe in this case would be equal to 1 full wavelength and a quarter. So 1 full wavelength and a quarter would be 5 lambda over 4. And this of course is our third harmonic. And the third harmonic is known as the second overtone. Remember, if you have more overtones playing over each other, so you have the first harmonic, second harmonic, third harmonic all playing at the same time, it improves the quality of the sound. Doing our equation again, C equals F lambda. F3 then equals C over lambda, which is C over 5 lambda over 4, which can be written as, have I done that the right way around, 5 lambda over 4, which can be written as 4, oh hang on, 5L over 4, 5L over 4. Oh, hang on, I didn't write that. What I didn't do here was L equals 5 lambda over 4. So lambda equals 5L. Sorry, lambda equals 4L over 5. I forgot to write lambda in terms of L. So this should be a 4 and this should be a 5, which makes this equal to 5C over 4L. So that's our equation for the third fundamental frequency. Now just like before, if you look at this bit here, we've C over 4L. That's the same as F1. So we can say that F3 is equal to 5 times F1. So our fundamental frequency could be 20 Hz. Our second harmonic is 3 times that, would be 60 Hz. And our third harmonic would be 5 times F1, which would be 100 Hz. So the reason I'm showing you this is that you don't just double the fundamental frequency to get the next harmonic. In this case, our harmonics are odd. Harmonics are odd multiples of the fundamental frequency. So if the fundamental frequency is F, the next harmonic is 3F, the next harmonic is 5F, and the next harmonic is 7F, and so on and so on. So hopefully that makes sense, and we'll see that. We'll try an exam question maybe tomorrow, but you'll see that come up quite a lot. So let's just look at an example question that's in your book. What I suggest you do with these is always do a little sketch or a drawing, because it just helps you see what's going on. So we have a closed pipe, and the length, what is the length of the pipe required to produce the first harmonic when the fundamental frequency is 256? So the fundamental frequency, I put a 1 there for the, say it's the first harmonic, is 256 Hz. The speed of sound, C or V if you want, is 335 meters per second. Ignore the end correction factor. We haven't talked about the end correction factor, so you can ignore that in all the questions. So basically they're saying, well, what length must this pipe be in order to produce this frequency, given that it's the fundamental frequency, so the pattern is going to be like this. Well, what do we know about this? Well, we know the length is equal to a quarter of a wavelength. So that means the wavelength is 4 times whatever L is. But first of all, let's find out what lambda should be. Well, C equals F lambda. So lambda equals c divided by f. So if the frequency is 256 and the speed is 335, lambda will be 335 divided by 256. Lambda will be equal to 1.309 meters. So what length of pipe would we need to produce that? Well, our pipe has to be equal to lambda divided by 4. So the length of pipe should be 1.309 divided by 4, which is 0.33 meters. So in order to answer these questions, you need to know the diagrams above very, very well, because if you can draw that out, it's really easy to see, well, what's the relationship between L and lambda.